The final application that we're going to consider of regression analysis in a financial context is a model for analysing non-stationary and potentially co-integrated variables. That is, we're going to examine the lead-lag relationship between spot and futures prices, more specifically between spot and futures returns. Now, given the kind of weak form of the efficient markets hypothesis, and given that I've previously said that spot and futures markets are really markets for the same asset but with different delivery dates, then we would expect the correlation in the change of the log of futures prices and the change of the log of spot prices to be very high, and in particular it should be close to 1. So we would expect that if new information hits the spot and futures markets, that information would be quickly impacted into the prices in both markets. So therefore we'd expect the price movements to be very similar in both of those markets because, as I say, they're markets for the same asset but simply with delivery dates. Similarly, if the markets are efficient, we would not expect spot or futures returns to react more quickly than the other one to new information that hits the markets. So in other words, it should not be possible to predict next period futures returns on the basis of lagged spot returns, or to be able to predict next period spot returns on the basis of lagged futures returns. So in other words, we'd expect correlations between the log of changes in futures prices and the lag of changes in the log of spot prices, that is, current futures returns and lagged spot returns. We'd expect those to be uncorrelated, and we'd also expect lagged futures returns and current spot returns to be uncorrelated. So in other words, we shouldn't be able to take information that's already available at some time t minus k or t minus j from one market and use that to help to predict future values of the spot or futures returns in the other market. Now, obviously that's one implication of the efficient markets hypothesis in its weak form, and we can test this idea by examining whether there are lead-lag relationships between spot and futures returns. Now, I've just said that the change in the log of futures prices we could call futures returns. Now, that may or may not be something that you've come across in other courses, but more specifically, I'm sure you're already aware of the possibility that we can calculate returns as being the difference in the prices between time t minus 1 and time t divided by the price at time t minus 1. But there's also another way to calculate returns, and we could define the return as being the change in the log of the price. In other words, that would be the log of the price at time t minus the log of the price at time t minus 1, which obviously is also equal to the log of pt divided by pt minus 1. Now, these are two different approaches that we could use to calculate returns, and the first of these we could call the method of calculating simple returns. In the second case here, these returns can be interpreted as continuously compounded returns. Now, for many reasons that I won't go into now, it's often much easier in practice to work with these continuously compounded returns than it is to work with simple returns. So the change in the log of capital ST is the spot return, the change in the log of capital FT is the futures return, and I'm going to use those terms from now on. Also, another small piece of terminology that we need to know for when we are examining the material in this study, the natural logarithm ln of the spot price, which is denoted by capital ST, I denote by a lowercase st. And similarly, the log of the futures price, ft, I denote by a lowercase ft. So the lowercase letters here denote the natural logarithm of prices. And one final thing to note about this course is whenever I've spoken about logarithms, whether I've used the notation ln or log, I'm always talking about natural logarithms. We're never interested in this course, and in fact in finance more generally, about logarithms to base 10. So what we're going to do now is examine two related studies that look at lead-lag relationships between spot and futures markets. The results of these studies are interesting for two reasons. First of all, they give us an idea about whether the efficient markets hypothesis is supported by these spot and futures returns or not. And secondly, if the efficient markets hypothesis appears to have been violated, then it may be possible to develop a forecasting model and therefore a trading rule to use information from the market that reacts the most quickly and to apply that information to develop a trading rule for the other market that reacts more slowly. So we're going to look at these two studies. The first paper by Tse, which was published in 1995 in the Journal of Forecasting, and the second paper, which I was involved with and which in fact started its life as an MSc dissertation, was published in the International Journal of Forecasting in 2001. So I'm going to talk about both of these papers together, although we'll focus on the second of them, and in fact the results for the two studies were very similar to one another and the approaches were also very similar. Now the first paper, the 1995 paper, used just over 1,000 daily observations on the Nikkei stock average, stock index and the corresponding stock index futures contracts from December 1988 up to April 1993. Now, it's all very well to use daily data, but if there are lead-lag relationships between spot and futures returns, in other words, on the surface it appears that there could be some informational inefficiencies in one of those markets, then we wouldn't expect those inefficiencies to last very long. So, in other words, there could be lead-lag relationships in existence, but if we use daily or weekly or monthly data, we might not be able to actually observe those effects because they've kind of become washed out, if you like, when we aggregate up to the daily or weekly or monthly level of data. So in our study in 2001, we used just over 13,000 10-minutely observations, and ours were on the FTSE 100 stock index and the corresponding stock index futures contracts for all trading days in a roughly one-year period from June 1996 to 1997. So once again, comparing between these two sets of data, obviously the first study examines a much longer period of time, but because the frequency of observation is much lower, it may be that the effects that we see have kind of been washed out or reduced compared with the effects that we might observe if we use 10-minutely data. So if we want to set up a model that relates spot and futures prices, the first thing we need to think about is what does financial theory tell us about what the relationship between spot and futures prices should be? Well, one theoretical model for the relationship between spot and futures prices is given by the cost of carry model. And we could express the cost of carry model for a financial asset as Ft star equals St multiplied by E to the power of R minus D multiplied by T minus T. So what does that formula mean? Well, that means the fair futures price, capital Ft star, is given by the spot price, capital St, multiplied by the exponential number E raised to some discount rate, and the discount rate is given by R minus D, where R is the continuously compounded risk-free rate of interest, and D is the continuously compounded dividend yield that's paid to holders of the spot index, and big T minus little t is the time to maturity of the futures contract. Now, because it's easier for us to work with a linear kind of additive model than a multiplicative one, we take that first expression at the top of the slide and take logarithms of it. So we take logarithms of both sides of that expression, and we use the notation that I just wrote on the board. That is, for example, lowercase st equals the logarithm of capital St. And then we have lowercase ft star equals lowercase st plus the cost of carry term, which is given by R minus D multiplied by the time to maturity. Now, if we want to use ft and st in an econometric model, the first thing that we need to do is to ensure that those things are stationary before we can validly use them in our model. Because we know if FT or ST, or rather the log of the spot price and the log of the futures price are non-stationary, then we can run into potentially serious problems if we use those in their raw or levels form in the regression model. So, and one other thing to note as well is that obviously in practice we don't actually observe the fair futures price. What we do instead is to use the actual traded futures prices that we've obtained from the markets. So the first thing we're going to do is to examine the log of the futures price and the log of the spot price to see whether those two things are stationary or not. So what we do is to run the Dickey-Fuller test regression on the log of the futures prices and the log of the spot prices first of all. So if we do that, if the test regression contains an intercept but no deterministic trend, then the appropriate critical value is minus 2.86. And remembering as well that the rule for rejecting the unit root null hypothesis when we use a Dickey-Fuller test, and once again I'm not saying the test statistic follows a normal distribution or a T, but let's just say it follows some distribution like this, the whole of the 5% rejection region here will be in the lower or left-hand tail, so the critical value here is minus 2.86. And if we look at the values of the test statistic for the log of the futures price and for the log of the spot price, those are minus 0.13 and minus 0.73 respectively. We can clearly see in both of those two cases that we do not reject the null hypothesis. So the null hypothesis, remember, was one that there was a unit root in the series that we were investigating, that is the log of the spot price and the log of the futures price, and we don't reject that null hypothesis. What we should then do as our next step is to move up a gear and run the test regression on the differences of these variables. So we run a regression on the differences of the log of the futures prices and the differences of the log of the spot prices. And obviously the differences in the log of the futures prices are the futures returns. The differences in the log of the spot prices are the spot returns. So when we run the Dickey-Fuller test on these, we can clearly see that the test statistic values of about minus 85 and about minus 114 clearly lie in the rejection region. So our conclusion from this analysis, which is a very strong conclusion, is that the original log spot prices and log futures prices were I1 variables, but the spot and futures returns are stationary series. That's what we would have expected, and that's what we find of any sets of asset prices and asset returns that we were to analyse. The prices and the log of the prices are non-stationary, the returns are always stationary. What does that mean for our model? Well, that means that it's not valid to use the log of spot prices or the log of futures prices in the regression model. We must, in the regression model, use the differences of those, that is the returns. So it's valid to estimate a model for the returns. It's not valid to estimate a model for the log of the prices. But the problem that we face, as I've said before, is that if we use a model that only contains first difference terms, then that model will not allow us to get any idea of whether there's a long-term or equilibrium relationship between the spot and futures prices. And the financial theory given by the cost of carry relationship would suggest that there should indeed be a long-run relationship given by that cost of carry expression. So the way that we get around that problem, and also at the same time to be able to build a valid econometric model, is to determine whether there is a co-integrating relationship between the log of the spot and the log of the futures prices. So the next stage in the analysis is to run a potentially co-integrating regression where we regress the log of spot prices on a constant and the log of futures prices. Now, an obvious question to ask is, well, why do we regress the log of spot prices on the log of futures prices and not regress the log of futures prices on the log of spot prices? In other words, why is ST on the left-hand side of this formula and FT on the right-hand side? Why are they not the other way around? Well, the answer is, again, as I alluded to previously, one disadvantage of the Engel-Granger approach to using non-stationary variables and testing for cointegration is that the approach forces us to choose one of the variables as being the dependent variable and the other variable or variables as being the independent variables. So we have to say that one of the variables is the dependent variable. And for reasons that we'll explain later, in the context of spot and futures markets, it makes more sense to have ST as the dependent variable, even though in the cost of carry relationship, ST and FT were actually the other way round. So what we're going to do is to run a regression of the log of the spot price on a constant and the log of the futures price. We'll then collect the residual from that potentially co-integrating regression, and we'll test that residual to examine whether it's stationary or not. So let's have a look at the estimated coefficients and the result of applying a Dickey-Fuller type test to the residuals of that model and see what we get. So the first thing is, let's have a look at the coefficient estimates, and the estimated intercept is 0.13. Now, in the model that we're using here, we haven't explicitly included a cost of carry variable in the potentially co-integrating regression. So that cost of carry term, R minus D multiplied by big T minus little t, will end up being pushed into the intercept. So the kind of cost of carry term is being embodied in that estimate of 0.13. Also, the financial theory given by the cost of carry relationship suggested that the estimated value of the slope coefficient in that regression should be approximately 1. And we can see here we've got a value of 0.98, which is clearly very, very close to 1. So that seems to support the theory, or that seems to be roughly what we would have expected. Now, we might have been tempted, given this value of 0.8, we might have been tempted to try to run a hypothesis test to test whether the true value of that parameter, gamma 1, could be 1 or not, plausibly. But again, as we said before, because we've got non-stationary data in the regression model, it's not valid to conduct any hypothesis tests about the value of this parameter. So notice in this table, I haven't even put any standard errors or t-ratios because it wouldn't be valid to interpret those. So given these parameter estimates, all that we can do is look at their values and say whether we like those values or not. Are the values plausible or not? We can't test any hypotheses about them. What we can now do is examine the result of the Dickey-Fuller test applied to the residuals of the potentially co-integrating regression. Now, the test statistic value here is minus 14.7. Strictly speaking, of course, this should be called an Engel-Granger test because it's the Dickey-Fuller test applied to the residuals from the potentially co-integrating regression. Now, once again in this case, because we are analysing the residuals from an estimated model rather than applying the Dickey-Fuller test to raw data, the critical value will be slightly different to the one that we would have got if we'd applied the test to raw data. And more specifically, the critical value would be more extreme. That is, it would be more negative than the minus 2.86 that we had before. So the critical value might be, for example, minus 3.5 or something like that. But the result of the test in any case is very, very clear. Clearly, the conclusion is that we reject a null hypothesis of a unit root in the potentially co-integrating regression residuals. The test statistic clearly lies in the rejection region. What does that mean? Well, that means that the residuals from the estimated regression model can be considered stationary. Another way to say that is that we took a set of log spot prices and log futures prices, and we found a linear combination of those two variables that was stationary, even though the original variables were non-stationary. So that means there is indeed a co-integrating relationship between those two variables. So given that there is a co-integrating relationship between the two variables, that means that we can go ahead and formulate an error correction model that includes the lagged value of that residual, which is the lagged deviation from equilibrium in our regression model. So that will be the kind of next stage, if you like. So the final stage in the Engle-Granger two-step approach is to form the error correction model. Now, the error correction model that we estimate in this case is slightly different from the one that we might have usually have expected in the past, given what I said about error correction models. Now, given what we've done already on error correction models, the error correction model that you might have expected could have been something like delta log st equals beta 0 plus delta z hat t minus 1 plus, well, let's say alpha 1 delta ln capital Ft plus some disturbance term for consistency, let's call that Vt. So this might have been the error correction formulation that you might have expected given what we've said before. But we've got something slightly different in this case. In fact, we've got something slightly different in two regards. The first difference is that the model that we would have expected did not include a term in the lagged spot return. So in other words, the model that we're actually using includes beta 1 multiplied by delta ln st minus 1. In other words, it includes the lagged spot return. Now, we can think of the model that we're actually using here as being a slightly more general one than this one, where we allow the lagged spot returns to influence the current spot returns, or the current changes in the log of the spot price. So it's like a slightly more general form of the error correction model than we've seen previously. The second difference is that we might have expected the change in the log of the futures price at time t, or the current period futures return, to be the one that's the independent variable in this regression model, rather than the lagged futures return. Well, the reason, in fact, that we include the lagged futures return rather than the current one in the model is that in the model that we actually estimate in the papers and the one that's given on the slides, everything on the right-hand side of the model is something that at time t is already known. So suppose I'm standing here in the financial markets, as it were, at time t minus 1, and I've observed the values of all variables at time t minus 1. So I know the value of z hat t minus 1, the st minus 1, and ft minus 1. So given that I know the values of all of the variables on the right-hand side, if I have parameter estimates for beta 0, delta, beta 1 and alpha 1, then I can use those parameter estimates together with the lagged values of the variables that I know on the right-hand side to make a real-time prediction of the next period spot return. So if the model only includes lagged values of the variables on the right-hand side, then I can make real-time predictions of the next period spot return. Obviously, if I were to use a model like this one here, I've got the current value of the futures return over here. So if I'm standing today at time t minus 1, I don't know what the value of this variable is. So in order to be able to predict the spot return at time t, I'd also need to know the value of the futures return at time t. And it's probably likely in practice to be just as hard to forecast this as it is to forecast this. So obviously, if this appeared in a lagged form, if there's a t minus 1 in here, then that's okay, because at time t minus 1 I know what the value of this is, so I can then use that in my prediction. So those are the reasons why the error correction model that we actually use is slightly different from the one that you might have seen before. So just before we move on, let me write down on the board the model that we actually estimate. So we've got delta log st, the log of the spot the delta log st, the spot return as the dependent variable. Then we've got plus beta 0 plus delta multiplied by the lagged disequilibrium term in here, plus beta 1 multiplied by the change in the log of the spot price at time t minus 1, plus alpha 1 multiplied by the change in the log of the futures price at time t minus 1, plus the disturbance term Vt. So this is the model that we're actually going to use. Okay, so now we know what the model is. We've got the equilibrium or error correction term estimated, z hat t minus 1. The next stage is to actually go ahead and estimate this error correction model over here. And if we estimate the values of these parameters, the values that we get are given in the table together with their t ratios. So the first important thing to note is now all of the variables in this model here are stationary variables. So therefore it's perfectly valid to conduct hypothesis tests about the values of the beta 0, delta, beta 1 and alpha 1 parameters that we've got in that model. So I can now put a column of t ratios and we can perfectly validly examine and interpret those. So the first thing to note is that all of the t ratios here on the slopes, we don't really care about the intercept value beta hat 0, but the t ratios on all of the slopes mean that those variables are very highly significant. Those t ratios are clearly very big in absolute value. Now, we may say, well, that means that the model is good because we found some variables that significantly explain the spot return at time t. And to some extent that's true, but we also need to be aware that when we estimate econometric models with very, very large samples, and in this case we've got about 13,000 observations, in these cases it will be the case that the standard error estimates for the parameters will be very small by construction. We know that the bigger the sample size, then the smaller the standard errors will become. So whenever we've got large sample sizes, we always get small standard errors, and that means we'll always have large absolute values of the t ratios. We could say, thinking about it in a positive light, that that means that the tests are very powerful in this case, and I guess that's true, but equally, one implication of that is that we always end up rejecting any null hypothesis that we want to test. So if, for example, I was to test a null hypothesis that the true value of beta 1 was 0.2, even though our estimated value of 0.1799 is very, very close, I bet if we tested that null hypothesis, we'd end up rejecting it purely because these standard errors are so small, we end up rejecting any null hypothesis that we want to test. But if we now leave that aside, we can see that alpha 1 and beta 1 estimates are both positive and very significant, whereas delta is negative and highly significant. It turns out that in all cases these estimates that we get are plausible, and these are the appropriate signs for the variables to have. If we now examine the signs of each of these variables and think about what that implies about the spot returns and about the right-hand side explanatory variables, first of all, looking at alpha 1 hat is positive and highly significant. What was alpha 1 hat? Alpha 1 hat was the term on the lagged futures return here. Now, if that's positive, that means that on average, the sign of the spot return in the next period is going to be the same as the sign of the last period futures return. So if the futures return at time t minus 1 is positive, on average, the next period spot return at time t will be positive. If the futures return at time t minus 1 is negative, on average, the spot return during the next period at time t will be negative, and so on. So what does that suggest? Well, this being statistically significant implies that there is a lead-lag relationship between spot and futures returns, with the futures market leading the spot market. So the spot market at time t is still reacting to information that was available to the futures market at time t minus 1, i.e. in the previous period. What about beta 1? Well, beta 1 hat is also positive and highly significant. What was beta 1? Beta 1 was the term on the lagged spot return. So this being positive means that the sign of the lagged spot return and the current spot return on average or most of the time are the same. What does that mean? If the time t minus 1 spot return is positive, on average the time t spot return will be positive. If the time t minus 1 spot return is negative, on average the time t spot return will also be negative, and so on. That's indicative of slow adjustment or underreaction of the spot market to information. That means if information hits the markets, hits the spot market now, some of that impact of that information will occur immediately, but there will also be some lagged adjustment so that the market is still reacting to that new information in the next 10-minute period. Finally, the hardest parameter to be able to actually interpret in practice is the delta parameter. Now, the delta parameter is the parameter on the error correction term in the model. Now, it turns out that a negative sign on that is in fact exactly what we would have expected in the regression model. Now, why would we have expected a negative sign? Well, it turns out that a negative sign is necessary in order for the equilibrating forces to be working in the correct direction. If we think about what is z hat t minus 1, z hat t minus 1 represents the disequilibrium between the log of the spot price and the log of the futures price that occurred in the previous period. So z hat t minus 1 is the difference between the actual value, st minus 1, and the fitted value from the model, s hat t minus 1. Okay, by definition, because this is a residual from the potentially co-integrating regression. If we then replace s hat t minus 1 with the right-hand side of the fitted values that we had from the expression, we'd have st minus 1 minus gamma 0 hat minus gamma 1 hat f t minus 1. So obviously, as I said, we can think of this as being the disequilibrium or the deviation from the cost of carry model that existed in the previous period. Now let's think for a second what that would mean if the residual was positive. Well, obviously, if this residual was bigger than 0, then that would mean this thing down here was also bigger than 0. And the implication of that would be that st minus 1 would obviously be bigger than gamma 0 hat plus gamma 1 hat ft minus 1. So what this would be saying is, if z hat t minus 1 is positive, then the spot returns, the log of the spot price at time t minus 1 is too big compared to its equilibrium value related to the futures price. So what should happen in order to restore equilibrium? Well, if we assume that the movement occurs in the spot market rather than the futures market, then in order to restore equilibrium, the value of the log of the spot price here must fall. In other words, the spot return must be negative. So if z hat t minus 1 is positive, the delta coefficient here is negative, so that means the change in the log of the spot price will be negative, because we've got a positive multiplied by a negative, which means this will be negative. What does that mean? If this is negative, that means the spot return is negative, i.e. the log of the spot price is falling. And that's what we need to restore equilibrium in this case. What about if this was less than 0? In other words, what if the residual at time t minus 1 is negative? Well, clearly that means that st minus 1 minus gamma 0 hat minus gamma 1 hat ft minus 1 is negative. That must mean that the spot price at time t minus 1 was too small relative to its equilibrium value given by the cost of carry model. What must happen to restore equilibrium here? Well, again, if we assume that adjustment occurs in the spot rather than the futures market, what must happen to restore equilibrium must be that the log of the spot price must rise. This has to go up to restore an equality here. So does that happen in practice? Well, the answer is yes, it does. Because obviously now z hat t minus 1 is negative and delta is negative, so we're multiplying a negative by a negative, so we get a positive. So that means that delta is negative, the residual is negative, the next period spot return will be positive. In other words, the log of the spot price must go up, and that's exactly what we need to restore equilibrium. So this kind of gives you an insight into how equilibrium or error correction models actually work. And you can see from this little piece of analysis here that in practice this term will always work to push the system back towards the equilibrium model given by the cost of carry. So it might be in every time period that the log of the spot price changes, the log of the futures price changes, all the disturbances here could all work to push the system away from equilibrium, i.e. they could disturb the cost of carry relationship, but at the same time there will always be this variable in here which will be the one that pushes the system back towards equilibrium. So as I said before, I think that means that the error correction model is a very clever one indeed, and it's something that's in fact very useful in practice. So what we've done now is to develop a model that has some very, very significant parameter estimates in, and where the variables on the right hand side are things which we know before the time period that we're currently interested in. So in other words, we've got a set of variables which potentially we can use to build real-time forecasts of the next period spot return. So what we do now in the paper, and what I'm going to talk about now, is using the lagged information on the right-hand side of this model to produce forecasts of the next period spot return. Now, the way that our studies actually look at this is to estimate a set of forecasts for the spot returns, but for a time period outside of the original estimation sample, which is called an out-of-sample period, but also this is a sample period where we actually know the true values. So we can compare the forecasts of the spot returns with the actual values. And obviously, if the spot return forecasts are close to the actual values, the models produced accurate forecasts. If, on the other hand, the spot return forecasts are a long way from the actual values, then those forecasts have been relatively inaccurate. Now, obviously what we do is to produce forecasts for a number of different time periods, and then we need some measures which aggregate the forecast accuracies, or rather they aggregate the forecast errors into one single measure that gives us an idea of whether all of the forecasts taken together were accurate or not. And two approaches to aggregating these forecast error measures are given in the paper. The first of these is what's called the root mean square error of the forecasts. What we do there is to calculate the forecast errors, the differences between the actual and forecasted values. We square them, we take the average of those squared forecast errors, and then we take the square root of that average, and that's called the root mean squared forecast error. Another approach we can use to aggregating the forecast errors is to calculate the absolute value of the errors. So we take the absolute differences between the actual and forecasted values and then take the average of those, and that's called that mean absolute error, or MAE. Now, if we look at the root mean squared error and the mean absolute error for the error correction model that we've just estimated, this one here, the ECM, then the numbers that we see here don't really mean anything to us. They're not in any particular scale. So whenever we produce forecasting models, a nice way to evaluate the forecasts, and a sensible way, is to compare the forecasts of that model with forecasts from other possible competing models. And we compare 3 other possible competing models here. The first other model is an error correction model, but with an additional variable that incorporates the cost of carry. So this is an identical model to the one here, but with an explicit term in the cointegrating regression, which incorporates the cost of carry term. Finally, 2 other approaches are ones which I don't really want to talk about. One is called an autoregressive integrated moving average model, which is simply a model which forecasts current spot returns as a function of lagged spot returns and also of lagged values of a disturbance or error term. So that doesn't include an error correction term. And finally, another model is called a vector autoregressive model. And this is another model that doesn't include an error correction term and which is a kind of system of equations. If we look across these four models, we can see that the error correction models, or the models that allow for this long-term equilibrium relationship to actually exist, are the ones that produce the most accurate forecasts. So we could conclude that these are the two best models to actually use in practice. One of the problems with analysing what we call statistical loss functions, that is things like mean squared error and mean absolute error, these statistical error measures don't really give any useful indication of how practically relevant the model is. That is, we can have a situation where the model appears to be very accurate from a statistical point of view, but it's practically not very useful at all. Now, as we'll see in a minute, the particular use that we want to make of this model is to develop a set of technical trading rules to tell us when to buy into or move out of the FTSE market. And it turns out that one simple measure that's been found to be very closely correlated with actual trading profitability is the percentage of times that we correctly predict the direction of the change in price. In other words, the percentage of time that we correctly predict the return will be positive when it is positive, and the percentage of times we correctly predict the return will be negative when it is negative. Now, if we look at the percentage of correct direction predictions for these four models, we can see, first of all, they're higher for models that incorporate the cost of carry than for models which do not. But secondly, we can see that in all four of these cases, the percent of correct direction predictions is very high. Now, that may lead you to think that we're doing very well here, because obviously if we just flipped a coin to tell us whether we expected the returns to be positive or negative, we'd expect to be right roughly half the time or 50% of the time by chance alone. But it turns out that if the market is trending, and in this particular out-of-sample period, which is 1 month, that we used roughly in June 1997 for producing these forecasts, the market was very strongly trending. That was the middle of a very long bull run. So that meant that if you simply said, I'm going to predict the return in every period will be positive, then you would do much better than getting their sign right 50% of the time. So the percentage of times that we correctly predict the sign of the return, which is equal to the percentage of times that we correctly predict the direction of the price movement, the figures that we actually observe are not quite as good as they first appear. But in any case, what we're going to do now is to take the error correction model, ignoring the explicit cost of carry term, but use the first error correction model in order to develop a trading rule. So essentially what we've got here is a model which produces forecasts for the next period returns. So for example, we forecast that the return on the spot index in the next 10 minutes will be 0.005% or minus 0.3% or whatever. We then need a rule which maps those forecasts onto a kind of trading decision that tells us whether to buy or sell. So the way that we actually do that is to, well, obviously there are an infinite number of ways that we could do that, but the way that we actually did it in the paper that I was associated with that got published in the International Journal of Forecasting is to use a number of different approaches which were of varying degrees of complexity, if you like, and which involve varying degrees of kind of filter for the rules. So the simplest rule that we could envisage, given these forecasts of returns that we're producing, would be to say we're going to invest in the FTSE 100 index for every period where we expect the return in the next period to be positive. In other words, we predict the return in the next 10-minute period to be positive, i.e. we predict that the price will rise, so we'll buy into the index now. If we predict the return in the next 10-minute period will be negative, then if we were already invested in the market, then we sell out, and if we weren't invested in the market, then we maintain our flat position. So that's the simplest possible type of rule. But it turns out that when we use that kind of rule, we end up making an awful lot of trades, and that means we incur lots and lots of transactions costs. So the way that we can cut down the number of trades is to use a filter rule. So we say instead of buying into the FTSE 100 index every time we predict the return to be positive, instead we buy into the FTSE 100 index every time we predict the return will be not only positive but higher than some pre-specified threshold. And we use 3 different threshold values, each one of which is correspondingly more strict than the previous one. And obviously the more strict is the filter rule, the more of the time we'll be out of the market and with a flat position, and therefore the fewer transactions we'll actually be making, because we'll end up staying out of the market for most of the time. So we in fact examine 5 different trading rules altogether. And if we assume that we started off with a wealth of £1,000 which we invested into the index and we move in and to and out of the index according to our various trading rules here, then we can see that the terminal wealth, that is the amount of wealth that we get at the end, is very, very impressive. So over a 1-month period, our trading rules, before we allow for transactions costs, can turn a £1,000 initial investment into anything up to £1,156. So that's quite a lot of return, over 15% in just 1 month. If we annualise those returns, that is, we assume that we were able to replicate that performance for a whole year, then we can achieve an annualised return that's almost 200%. So that's fairly spectacular. But unfortunately, that gives a kind of exaggeration of how well the rules would have actually performed if we'd used them in practice for several reasons. The first of these reasons is that, in fact, as I said, the market was very strongly trending over that 1-month period. So even if we bought and held the index for the whole sample period, we hadn't dipped into and out of it according to our trading rules, we still would have received an annualised return of nearly 50%. That was just because the out-of-sample month that we looked at happened to be a time when the FTSE was rising very, very strongly. The second problem is that the way that we implemented our trading rules assumed that we were able to execute the rules at immediately the time that we wanted to. So if we predicted the spot return to be big enough that we wanted to buy into the index, we assumed that we were able to instantaneously execute the trades that are required to buy into the index. Of course, in practice, that's unlikely to be actually possible. So what we also did in the penultimate 2 columns of the tables is to allow for what we call 10 minutes of slippage time. That means we allow for 10 minutes of time between when we make our predictions and when the trades are actually executed in the markets. Now obviously 10 minutes isn't actually a lot of time to be able to execute the trades. So it's possible that to actually be able to replicate the strategies in practice, we would have needed to allow for half an hour or even an hour of slippage time maybe. Because in order to actually buy into the index, as I'll talk about in a minute, obviously the index isn't a single entity, so we may have to buy the stocks of a number of different companies in order to be able to replicate that index reasonably. But once we allow for slippage time, even of 10 minutes, then our forecasts lose their market timing ability. That is, if our forecasts are for the return to be positive in the next 10-minute period, but we can't actually execute the trade for another 10 minutes after that, then maybe the return was actually positive in the period we predicted for, but by the time we can actually execute the trade, the positive return has already appeared in the market and disappeared. And in fact, that's what happens. The returns fall substantially when we allow for 10 minutes of slippage time. The most important problem with these trading rules is that, as you'll see, they require an awful lot of trades. So, for example, for the buy and hold while the forecasts are positive strategy, we would have executed 383 trades in just 1 month. Now, analysts have suggested that appropriate transactions costs for retail investors investing in FTSE 100 stocks are of the order of 2% to 5%. So that means every time we we go into the market and buy, and then we leave the market and sell, that is, we have a round trip of buying and selling, we incur a transactions cost of 2% to 5%. And obviously that includes stamp duty, which is payable on shares, bid-ask spreads, and brokerage fees. So that means that you can see, obviously, if we make 500 or even 300 trades in a month, and we only get a return over that month of 15%, very, very quickly our whole initial investment of £1,000 is going to be completely used up in taxes going to the government and fees going to the brokers and market makers. So it's simply not feasible to be able to execute these very high frequency trades in financial markets. In fact, it's often the case that we can't develop useful and profitable trading rules for any frequency of data higher than about monthly. Now, one way that we could think of to kind of cut down the number of trades that we make is to apply a strict filter rule. But unfortunately, that doesn't work either, because the stricter the filter rule we apply, the more time we end up actually out of the market. And as I said before, this was a very strong bull market month. So on the whole, if we don't have any information to the contrary, we want to be in that market because the market is trending upwards. But if we use the filter rules, especially the strict ones, which cut down the number of trades the most severely, we end up being out of the market most of the time. So if we use the strictest filter rule, we end up most of the time being invested in the risk-free asset and being out of the market, and even before transactions costs, we end up with lower returns than if we just bought and held the FTSE 100 index for the sample period. So whilst we have a set of trading rules that appear on the surface to be very, very profitable, when we allow for slippage time and reasonable transactions costs, we cannot, net of transactions costs, find a set of trading rules that are able to beat a simple buy and hold strategy over the sample period that we investigated using these error correction models. So if we were to conclude these two studies that we've looked at, what do we find? Well, the most important conclusion is that we find that the futures market leads the spot market. That is, it's possible, at least from a statistical point of view, to use lagged information from the futures market in order to be able to predict next period spot returns. Now, at first blush, that might look inconsistent with the efficient markets hypothesis. But it turns out that that observation is not inconsistent with the efficient markets hypothesis at all. And it's not inconsistent with the efficient markets hypothesis for two main reasons. The first is a set of things about the way that the stock market works, which mean that it's likely that it will impact new information more slowly than would the futures market. The most important of these reasons is that the stock index is not a single entity. So if I want to buy and sell the FTSE 100 index, I can't just go out and buy the FTSE 100 index in the way that I could just go out and buy one FTSE 100 index futures contract. If I want to buy the spot index, I would in fact have to buy a replicating portfolio of stocks that closely track that index. So buying the FTSE 100 spot index might in fact involve making a number of different buy decisions at the same time. We probably wouldn't have to actually buy all 100 stocks in the index. We could probably replicate the behaviour of the index quite accurately with only 10 or 15 or 20 stocks. But even so, that means 10 or 15 or 20 separate trades to execute to end up with the same payoffs as the FTSE 100 spot index. Secondly, some components of the index are infrequently traded. So typically, those stocks which are at the smallest end of the size spectrum within the FTSE 100 index, in other words, the ones that are kind of at the bottom of the index with the lowest capitalisation weightings, are likely to be infrequently traded. Now, our data is high-frequency data, observed every 10 minutes. So during many 10-minute periods, there have been no trades for some of those stocks in the index. And that means that the index will continue to embody old information. What we might call stale prices might be present in the index. Secondly, it's much more expensive to transact in the spot market. As I said here, in fact, the transactions cost could be of the order of 2 to 5% in the spot market, whereas in the futures market, the transactions costs are much smaller than that. Finally, and this is a relatively trivial point, stock market indices are only recalculated every minute, and this obviously puts an upper ceiling on the speed with which new information can be impacted into the stock market. New information cannot be impacted into the spot market more quickly than every minute because the value of the index is only recalculated once a minute. The second conclusion from these two studies is that there does indeed seem to be a long-run or equilibrium relationship between spot and futures markets. That is, there does seem to be a cointegrating relationship between them. And again, that cointegrating relationship does seem, or deviations from that relationship, are useful in predicting next period spot returns. Finally, since it was not possible, after allowing for slippage time and transactions costs, to profit from the forecasts from models of this type, then the fact that these statistical relationships exist is not inconsistent with the efficient markets hypothesis, because for the efficient markets hypothesis to have been violated, we would not only have had to observe statistically significant relationships in models of this form, we would also have had to have been able to make positive abnormal returns after allowing for transactions costs and slippage time, and in this case clearly we couldn't. So the conclusion here is that the efficient markets hypothesis is not contravened by the model and the data that we've got in this case.